Hi, can you hear me?
Yes.
Okay. Okay, so we were doing a few problems of inversion last time. I plan to finish inversion today as much as possible so that we can, in fact, we'll start with combinatorics today itself. So, because I think the practice problems which I've shared for inversion, going through all of them will take a lot of time. And anyway, most of them are from shortlist, so you can always check the solutions offline later on. But just out of those, I'll discuss one or two problems which I think have some useful ideas to convey, but the rest you can try on your own. And also, I will generally I give you some time to think about these problems, but today I will just go through the solutions quickly, so we get more time to start with the next topic, which is combinatorics. By the way, important to mention, I sent the link to register for this year's Olympiad calendar. So I hope all of you have gone to that link and filled up the form, etc. Make sure to do that. I think the deadline is, I think 1 week from now. So just make sure to do that. Okay. So okay. So yeah, last time I think we have started to solve this question C, but then in that process I realized that we had missed to do one topic, which was the 10 constructions of various tendencies if we are given a point, line, and circle. So we started doing that instead. But anyway, I gave you enough hints and ideas about how to complete those 10 problems. So you can work it out. But then we can come back to this question C and solve it. So I already indicated one solution 2 lectures ago, which does not require inversion for this, but now we'll see how to use inversion for this problem. And that also, I think roughly I had shared the strategy that we want to follow. So maybe we need to recap this. It's been a while. So yeah, so this was the problem which we had to solve. So basically, we are given a triangle ABC with AB, right angle triangle with AB the diameter of the circle. And if we have the in circle, which I think it was called in this question. So this in circle is given gamma 1, and then considering the perpendicular CD, then we are considering these two red circles, which they are called gamma 2 and gamma 3, and such that they are tangent to the base AB, the CD, and the circumcircle. So these both of these red circles are tangent to these three objects. So that is how we actually got into the question of, in general, if you have three such objects given, like point, line, and circle, how you construct a circle which is tangent to all those three objects. So that is how we started on that. So, but hopefully once you have understood how to do that, you can do this construction also. And then what the problem, what is asking us to prove is that these three circles, the two red one and the blue one, all of them, of course, they have base AB as one common tangent, but they will have another common tangent at the top. That is what we have to prove. And to do that, we realize that it's enough to show that the centers of these three circles are collinear, because then that will mean obviously by reflection in the line of the centers, we will get other common tangent. So there, I mean, to do this problem with inversion, the strategy was we invert the whole diagram with respect to this in circle and see what happens to these two red circles. So the claim there was that if these two red circles, which are gamma 2 and gamma 3, after inversion, if I call them gamma 2 dash and gamma 3 dash, so they turn out to be concentric circles. And if that is the case, then it means that the original two circles will have to have their centers collinear with the center of inversion, which was the center of gamma. So now all you have to do is in the inverted diagram, the resulting circles of these two red ones are concentric. Okay. So for that, basically we are going to invert this whole problem in the in circle. and we have to see what happens to all the objects. So why in circle? I mean, when you have a question like this, you always have to start with the understanding that which object we use for inversion. So as you see, the nice thing about inverting in the incircle, and this applies to any triangle. There is nothing special about the right angle triangle also. I mean, it's something useful to keep in mind in general, that whenever you invert in the incircle, what is happening to the lines A, B, B, C, C, A. Okay, so if you imagine that. So in general, when we invert a diagram, I mean, all the objects are in the same, they can be drawn in the same diagram. So for example, I could draw here itself what is the inverted version of line AB. So for example, it touches the incircle at this point. So the inverse of a line is a circle passing through the center of inversion. So it will be just this circle. But the diagram will become too cumbersome to draw in the same place. That is why I'm drawing it separately. But in your mind, you have to imagine that the two diagrams are overlaid at the same place. Okay. So then, so if you just draw the whole diagram, so we just draw the inverted version of the diagram now, and you'll see how we are building this inverted diagram one step at a time. Just as the original problem is given one step at a time, right? First we are given lines A, B, B, C, C, A, and so on. So we will follow the same order to construct the inverted diagram. So the starting point is of course the circle of inversion that you have to choose. So okay. So I'm calling the center O1. So the first you have to choose line AB. So it will touch this circle at some point. So let me just call this point some name, maybe X. Okay, so I'm choosing the point X where the original line AB was touching my circle. And so the inverted form of that line AB will be this circle with diameter over X. Okay. And same thing can be done on the other two sides. So BC and CA, they will also be touching the incircle at some points Y and Z. And I can do the inversion, so I can construct the inverted objects Y and Z. Something like this maybe. And then for those also similarly the midpoint of O1 Y, or rather the circle with diameter O1 Y and O1 Z respectively. Okay, so these are the three lines of the original triangle. Now where they intersect pairwise, of course all of them intersect at O1, but the remaining points of intersection are going to be the images of the vertices for triangle. So for example, this line AB and BC, they are inverted images, which are these two circles, O1x and O1y. So wherever they meet, so this has to be the point B dash. And similarly, you can see that this is going to be A dash and C dash. Okay. Now, important to know here, note here that these three circles will have equal radius, right? Because all of their radii will be exactly half of the incircle's radius, because this O1x, O1y being diameters. Okay. So what that results in is, if you look at the circle A dash, B dash, C dash, what can you say about that? So for example, if you just consider the pair O1x and O1y, right? So here I'm interested to draw if I consider the midpoints or rather the centers of the circles temporarily. I don't need them later on, but for now just I'm showing them in the diagram. So if you see what is happening here, this line joining the centers by midpoints, and you see it will be parallel to xy, parallel and half of xy. Okay, and then also this O1 B dash is known to be it will also have the same perpendicular bisector. So basically, x B dash and y are collinear like this, and not only are they collinear, because the radii of these two blue circles are equal, they are equal in distance also. So basically, what this means is that this B dash is the midpoint of xy. Okay, and similarly C dash A dash. So basically, you will see that B dash C dash A dash are nothing but the midpoints of X Y Z, which means that circle A dash B dash C dash is the 9-point circle of triangle XYZ. Do you follow this?
Yes, sir.
Okay, so then what will its radius be? So it's a 9-point circle of XYZ, so its radius will be half of the radius of XYZ. But do you see that means that radius is exactly equal to the radii of these 3 blue circles. So in fact, the conclusion is that this circle AB, A dash, B dash, C dash is congruent to these other circles O1X, O1Y, etc. Okay. So in particular, we can look at O1X because I mean this O1Y, O1Z we don't really require much for this problem. But yeah, I mean here also roughly in the diagram you can see that the circle passing through this A dash, B dash, C dash is congruent to this. So all now we have 4 circles of equal radii. And why are you interested in this circle A dash, B dash, C dash? Because it is the inversion of the circumcircle. So the circle passing through ABC in the main diagram, its inverse image is the A dash, B dash, C dash over here. Okay. And again, referring back to the original problem, these 2 red circles which you are interested in, each of them is tangent to base AB as well as the circumcircle. So in the inverted objects of both of them are, so the base AB has become this first circle. Okay. And now what we have just discovered is that the circumcircle is A dash, B dash, C dash. So the 2 red circles are going to be eventually tangent to these 2 circles of interest. Okay. And so if that those red circles are going to be tangent to these 2 circles, where will their center lie? So the center has to lie on the line A dash, B dash. Is that correct?
Yes, sir.
So this much we know that the center of those 2 red circles has to lie on this A dash, B dash. But we need some additional information. So the original 2 red circles are also tangent to CD. So we have to introduce CD in this diagram now. Okay. So CD means that it has to pass through the inverted image of C. So it has to pass through C dash plus it's perpendicular to base AB. Now perpendicularity, as we understand, is just another way of saying orthogonality. So I mean the line CD will become a circle which is orthogonal to the image of line AB. So in other words, we are looking for a circle which passes through C dash, passes through O1 also, and is orthogonal to circle O1X because that circle O1X was the inverse of line AB. Okay. So basically, if I describe what is the inverted circle of CD, so line CD has to be inverted into a circle. So firstly, it has to passing through a circle. So first, it has to passing through. It has to pass through the center of inversion. Then it has to also pass through C dash because originally the line CD was passing through C, of course. And the third criteria is that it is orthogonal to the circle O1X. So by the way, when I say circle O1X, I am talking about the circle with diameter O1X. Okay. I don't have a third point on this circle, so I'm just calling it O1X. Okay, so the this whatever inverted image of CD has to satisfy all these 3 properties. Okay. So in particular, if you note, it is passing through O1 and it is also orthogonal to this O1X circle. So at the point O1, if I draw the tangent, so that tangent also has to have that line, the center of that circle. Okay. So I'm drawing a tangent at line O1, and I'm also drawing the perpendicular bisector of C dash O1. Okay. Because again the circle passes through both of these points. So wherever these 2 lines intersect, that has to be the center of my inverted image of CD. Okay. And then with so if I just call this point some K, okay, then I can take KO1 as my radius and draw a circle. These things I can go out of. So the circle with center K and radius KO1. Something like this. I mean, as I now I keep drawing the diagram, maybe it will start becoming harder to be accurate. But as far as possible, I'm trying to maintain the proportions. And if you are doing this problem in the exam, it is probably better to use Invariant compass for complicated diagram. But anyway, so now we have all the objects of interest for us. So the three circles, I mean the three original objects to which the red circles are tangent are all represented in the diagram now, right? So the line AD, the line AB, the circumcircle, and the line CD. So all of them are now present in the diagram. So these two circles of equal radii and this red circle. So we are interested in two circles which are tangent to all these three objects. Okay. So to construct this tangency, there is a very useful trick here. Okay. Which I mean, it is worth noting in general also whenever you have a diagram like this. So I have what I want to do. So if I consider the center of this circle O1 is if I call it some variable t, I'm running out of variables, but let us call it t. So imagine a parallelogram. So O1t, k, and some other point. So I'm basically constructing a parallelogram t O1 k and some point m. Okay. So I completed this parallelogram. And you will see that this parallelogram has some really useful properties. So, well, I think my diagram is already bad here. So my claim is that the point M is the one at which both my red circles are placed. So the red circle meaning gamma 2 dash and gamma 3 dash. The inverted images of my original two red circles, their center will be at point M. But I mean, as we already noted, that point M has to be collinear with A dash B dash. It doesn't put in this diagram. So already it is a bit. So actually, I'll erase the line A dash B dash because we don't require it in this proof, I think. But yeah, in a more properly drawn diagram, the A dash B dash and M would also look collinear. But anyway, for now we work with this. So now look at what is happening with this M. So MT, the distance MT, right? And if I just call this point n temporarily, which is Mn plus MT. Because of the parallelogram, this is equal to K over. And K over is nothing but the radius of my original red circle. So if I extend this over here, which variable I want to use so far? P. So KO1, which is equal to KP. Okay. So basically what is happening here, and here Mn plus Nt again, if you see Nt is equal to T01 because T is the center of this circle. So this is Mn plus T01, but because of the parallelogram, T01 is the same as Km. Okay, so I mean this is a whole chain of equation, but I hope you are able to follow. So Kp, which is Kp and Ko1 are the radii of the red circle. Then Ko1 and Mt are equal because of the parallelogram we just constructed. Then Mt is Mn plus Nt, and again out of that, Nt is equal to To1 because T is the center of the smaller circle. And finally, To1 is equal to Km. So if you compare the first and last term, what do you see? That basically out of Kp and Kp is obviously Km plus Mp, right? So cancelling Km from both sides, what I am getting is Mp equal to Mn. Or in other words, what does it mean Mp equal to Mn? Can you see what is the implication?
Its center M and P and line.
Exactly. There will be circle center M and with radius Mn, then that will be tangent here also, and it will be tangent here also. Okay. So this is one of our desired circle, but we still have to show that this circle is also tangent to the other blue circle. So yeah, I think for that I require to show that. So if I can show that this a dash b dash m are collinear, then you see it will automatically imply this purple circle is tangent to the other blue circle also, because these two circles are symmetric with respect to line a dash b dash, right? Sorry, I mean now I'll just hand you the diagram bit. But suppose I show that a dash b dash m are collinear, then do you see that it's enough to see this purple circle be tangent to the first circle? Automatically, it will be tangent to the other circle also. Okay. So for that, I need to show this a dash b dash m collinearity. So I'll just put it in to prove that this. But so you see, assuming that part, we have constructed one of the red circles of our interest. And now, in fact, not only this, we can do the same thing for the other circle also. So here we do the inner circle of tangency. But if I just zoom out, I can simply take the outer circle of tangency if I consider the other point here. So if I call this point Q, then I'm talking about the radius MQ. Okay. And I won't work out the calculation here, but you will see that even MQ will be equal to MK plus KQ. Okay. And then you can do the similar kind of transformation and eventually show that the circle with radius MQ is also externally tangent to the blue circle. Okay. So therefore, you get a circle like this basically. Okay. So now we have got, and both of these purple circles have center M. So the concentric part is being achieved. So I mean, I think so. The only thing left to be shown is this collinearity, A dash B dash M, because then that will uniquely define these two circles as the ones which are tangent to all the three objects. And then I mean, just going back to why this argument works. So after you invert it back to the original diagram, these two purple circles will become these two red circles, and but their centers will remain collinear with the center of inversion, which was the O1. So therefore, these three points end up being collinear. Okay, so I hope you followed the argument. If any part is hard to follow, just try to draw this diagram again one step at a time. And you realize how I draw this diagram. I don't suddenly come to this diagram and invert everything in one single shot. But just the way you construct the original diagram one step at a time, and like there is a chain of dependencies, right? You first construct one object, then you construct the dependent objects, and so on. So in the same way, we construct the chain of dependency here. What that does is it makes sure we are using all the information, because ultimately there is one what you can say universal truth about geometric transformations, and it is worth writing down. It is almost like conservation of energy, conservation of angular momentum. So this is conservation of information. So what inversion or homotheity or any of these things do, they transform the information from the original configuration to something else. But they cannot create or destroy information. Okay? So whatever was true in the original diagram, there will be some equivalent truth in the new diagram also. Okay. So by transforming, you will never add new properties or take away existing properties. You will only transform them from one domain to the other. And the advantage is that it is easier to see the connections in that transformed version, which were harder to see in the original version. Okay. But this is a very important principle. So that is why I make sure that all the information in the original diagram is transferred to the new one. Okay. So for example, the fact that the CD was perpendicular to AB, that fact was used in the orthogonality of these two blue circles, and so on and so forth. Okay, now that A dash B dash M collinearity, let me see. I think I missed to see that myself. Okay, but is the rest of the proof understood? So then I'll erase the purple objects which are like making things complicated for us unnecessarily. Now we only want to focus on the A dash B dash M collinearity. So again, to recap how we constructed this point M. So we completed the parallelogram O1 TK or T over K rather. So what we know is that this Km is equal and parallel to O1 T. Okay. And we have to use that somehow. Okay, yeah, I think I know how to do this. So what happens, right? In the I said this other two circles O1Y and O1Z we did not use them. So I think it is time to use them also. So if you see how we constructed the point K, it is a perpendicular bisector of O1 C dash. But do you see the perpendicular bisector of O1 C dash will also contain because basically just as this yellow line which I draw here, which is the XY which is passing through B dash. Similarly, I can draw YZ also, right? And it will pass through C dash just in the same way. Okay. And this YZ will be parallel to this red line, which is the perpendicular bisector of C dash O1. Okay. So here if I complete this diagram, what am I getting? So I am considering the centers of these two upper circles, O1Y and O1Z. So my claim is that this red line, which is a perpendicular bisector of O1 C dash, it will also pass through the centers of these two circles. Does that make sense? So it will pass through the centers of these two circles. And so what is happening? This line. Okay. So basically, what will happen, right? If you look at the center of O1Z, okay, if I call this point J, I don't have any variables now, but we can see that A dash J and O1T are also forming a parallelogram. Okay. So therefore, basically A dash J, B dash L, and T1. All three of them have the same relation with each other. Firstly, of course, they are equal in distance length because they are the radii of these three circles. But also with some angle chasing, you can show that they are equal and parallel. Okay. I'm skipping the angle chasing for now because it will take more time. But you can show that they are equal as well as parallel. So therefore, what it means that J and K as a whole, if I apply the vector O1T, okay. So apply the vector O1T to this. I will get the points A dash, B dash, and M. Okay, so therefore, of course, if J and K are collinear, then A dash, B dash, M are also collinear. Okay, so that finishes the proof. Okay, but yeah, in general, this was definitely complicated. Like first thing I also understand is why you have to think about inverting in the in circle. So that and followed by that, I mean, this was almost like because these two gamma 2 gamma 3 become concentric, this problem works. Otherwise, it is quite hard to follow that way. But that's why every time I give you an inversion solution, I always try to give you a non-inversion solution also. Okay? So that it is not like if you only know or if you don't know inversion, you are stuck. That should not happen. Okay, but I hope you follow the details, and basically this is a good example of how to apply inversion in given complicated situation and how to transform all the objects from the original diagram to the new one. Okay, any doubts in this? And also for your understanding, it is good to draw this diagram once on paper and once in GeoGebra also, because I mean, seeing this connection, it is okay to say on paper that this purple circle, I mean, it's almost a surprise that this center M, which is the center of both the inner and outer circles of tangency. So actually seeing that in a diagram is very useful. Okay, but I also keep this parallelogram trick in mind. So as I said that there's nothing special about this configuration. Anytime you have a circle like this, like anytime you have a configuration where there is a circle and you want to draw there's another circle over here, and you want to construct a circle which is tangent to both this circle and the given circle. Okay, so anytime that is there, you can consider this parallelogram. Okay, and the same calculation will happen here, just the way we did right now. Okay. But of course, the important thing for this is these two circles are intersecting at this point. Okay, so that was used to complete this calculation. Okay, then moving on to the next problem. So question D. So what is given here is, first there is a small circle C and a line L. Okay, and these circles C1, C2, C3 are tangent to each other as well as these two objects C and L. So diagram is quite complicated to draw. At first, you may not even realize that this is possible. Like in general, if you take any three circles C1, C2, C3, right, in the plane, yeah, I mean, if you start with this, like first you want to construct three circles that are tangent to each other, and now I want a circle tangent to all three of them. That is fine, but how do I construct a line tangent to all three? So it seems impossible. So it all depends on your starting three circles. So you can do it the reverse way. Let us start with the line first. Okay, so I start with any line. To this, I will first construct my three circles. Like this. And now I can imagine that there will be a fourth circle inside here, which will be tangent to. So now this configuration satisfies all my requirements. Okay, so this is my line L. This is my inner circle C. And then these are the three circles C1, C2, C3. Okay. And what is given is the radius of this inner circle is given to be 1. And you have to find the distance of the center of C from line here. Okay, so this distance, if I call it x, this is what I want to find out. So again, the question is, how can we use inversion here? There is obviously a lot of tangencies, so something interesting can happen, but how do you choose the strategy for inversion carefully to extract the maximum utility out of this? So the idea is this. Do you remember last time we had done Steiner chain?
Yes.
So we had two concentric circles over there, right? And inside those two concentric circles, we are embedding a chain of tangent circles like this. So you see the problem was kind of similar because you had two main objects here, the inner circle and outer circle. And then outside your chain of tangent circles, which are tangent to each other as well as these two objects. So if we in a way you can see this C1, C2, C3 would be those outer circles. So here in this diagram, I do 5 circles, but maybe with slightly different radius. Similarly, you can get a chain of 3 such circles, okay, which are tangent to each other, like this, something like this. So if I can convert this diagram into this diagram somehow, and then in that standard chain problem, we had already constructed the criterion under which this happens, right? So if I call this radius small r, capital R, there was some formula which we derived that what is radii should follow in order for such external circles to exist. So we can probably do some strategy around that. But to do any of that, the first thing is that these two objects have to be concentric circles. But right now, what is given to me is a circle and a line. So the first question is, can we convert this circle and line into concentric circles? And to do that, we can apply inversion. Because under inversion, what is guaranteed as these other 3 circles, C1, C2, C3, will remain tangent to the whatever inverted version of C and L will be. So we just have to construct the inversion which will take C and L into concentric circles. So how do we construct such an inversion? I'll give you a few minutes to think about this. So is the strategy clear that why we want to do this?
Yes, sir.
Okay. Okay. So specifically the challenge first is to find the center of inversion. Where should the center of inversion be located around which the C and L will become concentric circles. So I mean, for reasons of symmetry, I am thinking that we should start by looking for the center on this line itself, this perpendicular line. Okay, so it has to lie somewhere on this perpendicular line. But specifically, if you think about it, what we want to do, right? So we know that under inversion, the center doesn't go to the center. So there's no point in trying to map the center of the original circle into the concentric circle. But what we can try to do is map the diameter. So and by the way, for this, for temporarily, I'm not worried about these outer circles C1, C2, C3. Okay, so I'll probably just erase them from my diagram, and I'm looking at only the C and L. Okay, so simplifying my diagram to just the objects of interest. So circle C and line L, and the radius of the circle is given to be 1, and this height is unknown, so we'll call it x. Okay, and as I said, on this line perpendicular to capital L, I am trying to look for that center of inversion, and I am particularly going to look at the endpoints here. So A, B, these are of interest to me, and this point D. Okay. So vaguely you can imagine, like try to guess where that center of inversion has to lie for this whole diagram to make sense. So can you imagine what will happen if my center of inversion lies somewhere in the upper zone. So if I try to choose a center of inversion over here, what will happen? So you'll realize that things go wrong, because what will inversion do to these points A, B, and D, and if I call this point O. See, eventually I want the diagram to do something like this, that the whatever is the if A, we go to some points A dash, B dash, okay, and this line L will get inverted into a circle whose diameter will be O and the inverse point of D. So wherever is the inverse point of D, suppose it is here, it is D dash, okay, then the final diagram is to look something like this, that this O dash O, this O D dash and A dash B dash have to have the same midpoint. Only then will I say that these two circles are concentric. So O D dash and A dash B dash have to have the same midpoint. But for that, the order of the points is important. So if you took the point O above over here, you'll see that the order of the inverted points will be, firstly they all lie on the same side of O, right? So then they will look like O will be here. The farthest point will come closest, right? So if D is farthest from O, its image D dash will be here, and then B dash, and then A dash. So here the circle OD dash and B dash A dash are not never going to become concentric. Okay, so there is no point in choosing the center of inversion above. Okay, so then what you can try to do is choose the center of inversion below the line L. Okay, we still have to work out the exact distance, but I'm just giving the intuition that at least in the order of the points where it should be. So if the point O is chosen below, now can you see what will be the resulting order of the inverted objects? So if O is here, the closest point, which is D, will go the farthest, right? So D will go to some location D dash, right? And then B dash and A dash also. So here it seems that there is maybe a chance that by choosing this center O carefully, I can align all of these three objects in just the right distance, right? Where the midpoint of A dash, B dash, and the midpoint of O D dash will coincide. Okay, so if I call this length Y, so this X length is one unknown which you have to eventually find. But before we reach there, the first we have to find this distance Y. Okay, so where should this point O lie, such that after inversion, actually the circles will be concentric. Very important to realize, the circle of inversion is not concentric here. So the circle of inversion is some third circle altogether. But the images of the C and L are what you want to try to make concentric. Okay, so the image of C, which is A dash B dash, and image of L, which is circle OD dash. So these are the ones I want to try and make concentric. So can you try to compute the value of Y? And X is the distance from center to, so if I call this center O1, so O1D is what I am calling X. So there is only one variable in our whole question, X. So everything we have to find is in terms of X. So even Y, the formula for Y will be in terms of X. Okay, so how do we do this? So one thing is that the radius of inversion around O doesn't really matter, but just to illustrate that point, that why doesn't matter. Always I've been saying that the radius doesn't matter, but I want to show it in actual example. So if I take some radius r for my inversion, okay, then I'm interested in the distances of the inverted object. So if I draw the inverted object here on the right side, okay, so still not a straight line, but anyways, I'm only interested in the distances. So as I said, the order of the points will be A dash will be closest, then B dash, and then D dash will be the farthest. So given in the original problem, I can find out all the distances, right? How much is OD? So OD is Y. Then O1 will be equal to 5 plus 6. Therefore, OB will be equal to 5 plus x minus 1, and OA will be equal to y plus x plus 1. So I know I don't want O1 anyway, but these three distances I know. So through inversion, I know what will be the new distances, right? So if my radius is r, then OD will become, here in this diagram, OD dash, which will equal to r square upon OD, etc. etc. Each of them will be r square upon the original distance, right? And here the condition which I want, which is the midpoint of A dash B dash, should also be the midpoint of OD dash. You see, I can express that as OA dash plus OB dash by 2 equal to OD dash by 2, right? Or in other words, if I cancel out the 2, all I'm interested is in OA dash plus OB dash equal to OD dash, right? So if I find the value of y which satisfies this property, then I'm done. And now here you see why the radius of inversion doesn't matter, because each of them is simply r square upon OA plus r square upon OB equal to r square upon OD, and the r square simply cancels out. So it doesn't matter what r you choose. As I already said that it will only scale the whole diagram up and down, doesn't really change the relative configuration. So with any value of r, if these two circles are going to be concentric, they will be concentric anyway if you choose a different r. Okay, so basically, for convenience, you can assume that I have chosen the radius of inversion as 1. It will be the same thing. So all I am saying is 1 upon OA plus 1 upon OB equal to 1 upon OD. Okay, and this OB, OA, OD are given here. So actually, the whole equation turns out to be so what? So 1 upon OA is 1 plus 1 upon y plus x plus 1, y plus x minus 1 equal to y. So in this equation, I have to solve for y. Okay. So in the interest of time, I'll just copy the final answers. They are already found earlier today. So as it comes out, y is equal to root x square minus 1. Okay. Even if I give you some time, you can also work it out and get to the same conclusion. But I'm just saving some time for us. Okay. So y is root x square minus 1. Whenever you get an answer like this, of course, now you can plug it back in. And so, I mean, after this, it is just a few calculations, because now what we will do, we want to ultimately, so we found out the transformation which changes this diagram into this one. Okay, and in the Steiner chain problem, we know what is the relation between capital R and small r, and we have to use that to finish the problem. Okay, ultimately, we'll get the value of x. Okay, and it turns out to be a nice value integer. Okay. So there is no like square root, no, nothing messy happens there generally. But so we will do that part. But before that, whenever you get a solution like this, it is always good to pause and think that why we got x square root x square minus 1. Does it indicate some geometric interpretation of the problem? Okay. So I'll just look at the diagram for a few minutes and let you think. Can you see x square minus 1 somewhere in the diagram? Root x square minus 1. Is there any quantity in the diagram which is equal to root x square minus 1.
Sir, power of d with respect to c is x square minus 1.
Correct. So if I draw the tangent from point D to this circle, do you see its length will be root x square minus 1? This
Yes.
this tangent length will be exactly root x square minus 1. So what it means that this dt is equal to du. Okay. And by the way, what is the power of d with respect to point O? If I treat O as a point circle, then you see what I'm really saying, that d has equal power with respect to the circle C and this point O. Okay. So in other words, what does it mean? What is this line L?
Radical axis.
Yes, it is a radical axis of this point circle and this circle. Okay. So you see, I mean, you can. In fact, I did this later on. After I found this very nice answer, I went back and tried to see, can I solve this with pure geometry? And it turns out I can do it. So it is not hard to do that. Okay, you can with pure geometry also you can say that if I take the center of inversion O such that the line is the radical axis, then it turns out then under that inversion, this line and this circle C become constant. Okay. So anytime you do some algebraic calculation and you end up with a nice answer particularly, it is worth going back to the main diagram and seeing something whether it is working out. Okay. And in fact, you know what? Let me show this. It's very nice to see that this is working out. Okay. So suppose this is my starting circle C, and so I'll do it the reverse way. I mean, really in the given problem you have to take the line L first, but I'm just taking the center of inversion directly. So this point C is the center of inversion, and so I mean, as usual, if I construct the radical axis of these two, so for that I'm just going to construct the tangents, and I'll take the midpoint of the tangents. Okay. So if I take the midpoint of these two tangents, then this line, this GH will be the radical axis of the original circle and this this point circle. Okay. So these are my original objects. Okay, and now I want to take any circle centered at point C. The radius doesn't matter. Okay, and this will be my radius of inversion. And watch what happens to my these two blue objects. Okay, so I'll invert this blue circle in this, and I'll invert this circle. Look at that. You see how the two resulting circles are concentric, and doesn't matter when I move this original diagram, these two resulting objects are always concentric. Okay, they are very nice too. And in fact, if you remember when we did power of a point, we visited this configuration almost in the first exercise. So I mean, things which we do at the start of the this whole topic are coming back. But this is a very nice construction to see how those two circles are always concentric. But anyway, so yeah, point is that you can do that construction, and so in the given problem, again I'm saving us some time, so I'll just copy the main equations so that you don't have to do them here. But basically now what we want to do, I mean how we want to finish the problem. So we are interested in this. So we know not only that what is the transformation which will take this diagram into the new one, but we also know the small r and capital R, because they are nothing but the radii of my two circles. So in this diagram, if I work out this a dash b dash is the diameter of the inner circle, and o d dash is the diameter of the outer circle. So now I can substitute everything back and write down those values of those radii. So the inner radius, right, the radius of the inner circle, if I call it small r, its formula is 1 upon okay, and I'm just writing this for a reference so that in case you want to do it yourself, and I encourage you to do that, just as for verification that you are on the right track. If these like intermediate things are matching for you, then it means you are on the right track. And capital R is easy because it is simply diameter of like OD dash upon 2, and OD dash is simply equal to our R. So this is 1 upon 2 root x square minus 1. Okay. So you know smaller and capital R. And now if you go back to the Steiner chain problem where we had derived that, so we had derived for generally n circles in the outer chain. Here we have 3 circles, right? We have 3 circles C1, C2, C3, which are tangent to each other. And so that criteria happen to be R minus R upon R plus R equal to sine of pi by n. Where I mean here n is 3, so this is nothing but sine 60. So this is root 3 by 2 for us. Okay. So now basically now you know everything, because if I substitute the capital R and small r over here and solve the equation, I will ultimately get the value of x. So I mean, if you just do the simplification, finally I'll tell you the equation you get, which is x plus root x square minus 1 equal to 7 plus root 48. And just looking at this for the form, you can guess that obviously x equal to 7 is the answer. But if you in general you can solve this also, right? And if I take x on the other side, okay, then I can I can do this. I can take the square of both sides and simplify, etc. I'll get the same conclusion. But finally, the answer of this question is simply x equal to 7. So I mean the calculations are a bit ugly in the middle, but in the end everything cancels out very nicely, and you get x equal to 7. Okay. But I mean the numerical part is not important. The important part is the strategy. That I mean starting from the original statement, we spotted the opportunity to convert this into the Steiner problem first. Then we have to work out the exact transformation which does this operation. Okay. So we have to find out, and there also understand how we roughly blocked out where that center of inversion should lie. It cannot lie in the upper half. You can also see it cannot lie somewhere here. So it has to lie below the line. Then once we have that, then we actually found the distance of that point, and or we could have done it geometrically also, as you can see on your own. And then finally we use that inversion to transform all the given information into the new Steiner coordinates, and then this final part which we had done last time. So yeah, I mean, as I always say that these Olympiad problems are multi-part problems, and the difficulty is not in every individual step. It is to see what are those stepping stones. So if I split the original problem into 4 small parts, then everybody will get it. But over your practice and intuition, you have to develop how to see those intermediate steps, and then you can make faster progress. Okay, but with that, actually, I want to end this inversion topic, because there are more problems here also. But I feel that we have covered enough of them now, so I'll encourage you to try them on your own. And in case you get stuck, you can always look up the official solutions. This last problem doesn't seem to be from shortlist. I try to remember where it is from, or maybe I didn't design this. I took it from some textbook, I think. If I can find a reference where you can get this problem, then you can see the solution there. I think it is from Sharijin, probably. But anyway, I'll see that. Okay, so then I think that's all for geometry for now. We didn't cover everything in geometry, but you can say, roughly speaking, we covered all aspects of circles. So we did radical axis, poles and this coaxial circles. Cross ratio is actually not only about circles; it has more implication also. But then we also did inversion, poles and polars. So lot of theory revolving around circle. And what you have to see is that you already done a lot of theory around triangle, orthocenter, in circle, x center. So how the triangle theory and the circle theory connect to each other, and together they are very powerful. They can solve a lot of problems. And in a way, actually, there is much more theory also to be explored beyond just these two objects, like triangle and circle. Like conics in general, like ellipse, hyperbola, parabola, which you do study in coordinate geometry when you do in 11th standard. So they are like the general solution for the quadratic equation in two variables. So that is how you do study those objects, but you never study them geometrically. So and it may amuse you to know that these poles and polars are not applicable to only circles. You can talk about pole and polar of a hyperbola or a parabola also. So that is some really advanced geometry which we don't get into here because actually they don't ask this in Olympiad. So maybe in someday in the future if that changes we will discuss that also. But in case you are interested, you can read up about all of these things. Okay, so with that, let me switch gears completely to combinatorics now. Okay, so combinatorics, new topic, new starting point, and some of the things are what I said are true in combinatorics also, that a big problem can be broken down into several small problems, and you have to work it that way. One very important thing in combinatorics which you have to learn is presenting your ideas in a logical manner, because many times we have an intuition that something is true, and we are so convinced that what we are thinking is justification, but is it really a justification or we are trying to phrase it in English? Okay, so that is one difficulty we always find in people who in students, right? When they write the exam, they don't do a good job of explaining their logical ideas. So that is something we have to work upon. But broadly speaking, when I say combinatorics, what are the kind of problems I'm talking about? So I can say almost one family which is called counting problems, or there is a technical name, I think it's called enumerative combinatorics. So all kinds of questions which say how many ways you can do something. So any problem like distributing objects in boxes or any kind of things. So all of them are called enumerative combinatorics. And within this, we have a lot of techniques. So you must have already studied some of them, right? Some basic things like addition principle, multiplication principle, bijection, complementation, etc. Okay. So these are like the building blocks that, just as in geometry or axioms, in combinatorics, I don't know if it's anything can be called as axiom, but as a fundamental building block, these AP, MP, etc., they are the starting point. Okay. Then another important is inclusion exclusion principle. So have you studied this, by the way? Inclusion exclusion.
Yes, sir.
Okay. And there are some generalizations also. So in case we get some time, we'll get those also. So not only like generalizing to n set, that is obvious. Like a1, a2, dot, an is fine, but you can take it one step forward. So maybe like basically when I say mod of a1 union a2 union ak, I'm counting how many objects are in at least one of the sets. A1, A2, A2. But I can modify this question a bit and I can ask how many objects are in exactly k sets out of A1, A2, A2. Okay. So for example, if I have three sets like this, then what the union is counting is this whole area, right? But suppose I ask how many objects are in exactly one set out of all of these things. So then I am looking at only this area. This area. So which lies in exactly one set, not more, not less. Or if I ask the question, how many objects are in exactly two sets, then I'm looking at these part, etc. etc. So these are like more fine-tuned questions about any given configuration. So those are some kind of generalization of vision inclusion exclusion principle. So I don't know if you've seen these also, but in case you are not, then you can look at those. And then another important set of counting ideas is around recurrence relations. Okay. So recurrence relations, generating functions. So these are always the idea is that you have a larger problem and you try to break it into copies of itself, like smaller copies of the same problem. So this is one very useful idea. And then another idea which you already know. So we all know circular permutations, right? how to arrange objects around the circle. So if you have n objects, how many ways are there to arrange them around the circle?
n minus 1 factor.
N minus 1 factor. Right? So the important thing is that I'm assuming that if I rotate the objects around the circle, I don't consider that as a separate configuration. So there is a generalization of this also, which I can call counting under symmetry. Okay. So the idea is in the circle case, the rotation was the symmetry. That if you rotate the object around itself in any number of degrees, the object remains identical. But that is just one kind of symmetry. You get all kinds of symmetry in various cases. Like for example, that was a circular competition where there may maybe a necklace and some beads or some chairs around a table. But you can consider maybe there is a chessboard and I want to color the squares of the chessboard such that again I can rotate the chessboard around by 90 degrees, 180 degrees. Then the colors, the orders should be considered the same. So basically, if I keep the chessboard fixed to the table, so it cannot be moved, under that condition, these two coloring will be considered separate, right? But if I say that I can rotate the chessboard freely, then these two will be identical because I can rotate this 180 degrees to get this. Or similarly, flipping in the mirror images around. So I can flip the chessboard horizontally, vertically, etc., etc. So there is a lot of various symmetries that can be applied. Okay. So in general, how to count under the existence of symmetry is a very interesting topic. And have you studied some group theory? I don't know if you get introduced this in our regular MPI lecture, but the basic addition like A1, A2, A3, A4. Do you know these things? A1, M2, M3, M4, like commutativity, associativity, in existence of inverse, these things. Okay, probably not. But if we get the chance to do this, we can study a very interesting topic called group actions that applies all of these group theory to solve these kind of problems. Okay. And I think if there is this and probably just one thing to add. So combinatorics is about counting objects, rather this enumerative combinatorics is about counting objects. So the important thing is what are you counting? So in some cases you get things like you count number of objects to distribute in a box or whatever, etc. Or some ice cream vendor and all those things. But in many times the objects to be counted are themselves from a different domain. So combinatorics typically has a lot of crossover with other topics like geometry, because many times you may be asking questions like if you draw n lines in a plane, then how many regions have you divided the plane into? So there the objects you are counting are actually geometric objects, or how many triangles are there in a given anything like that. So combinatorics can have a lot of overlap in geometry or number theory also, because you get number theoretic questions also, like how many numbers are there which are divisible by this or are like co-prime to this, or any such question can be asked in number theory or even in algebra, because you can ask like how many polynomials or have this coefficient or anything. So the objects to be counted can be from any of the other domains. So you many times you get Olympiad problems which are combinatorics plus geometry, combinatorics plus number theory, so like that. Okay. So in those problems it is required to know that background of that topic also. So you don't require full number theory, but you may require some specific property, like maybe for co-prime numbers you require GCD and things like that. Okay, but so all of this is a brief recap, a brief overview of what I'm calling enumerative combinatorics, which is about how many so and so, where the answer is a number. But there is another completely different combinatorics which are I don't know, there is a name. So let us just call it non-enumerative combinatorics, okay? Which is prove that something. So prove that something is true. So like pigeonhole principle, for example. So here the question is about something exists or something doesn't exist, or some property like that. Okay, so what are the important techniques here? So pigeonhole principle is the one most important idea here, because just like you don't have axioms, but we have very important foundations of the whole theory. So pigeonhole principle is very important there. Okay. Then few other strategies. So when you want to look for an object, we have to have some strategy that how we can go looking for it. So one very important idea is invariance. So invariant is nothing but when you have a system which is changing, like maybe it is a game being played, or any transformation being applied. Okay? So then under the transformation, what are the quantities that don't change? Okay? Because the thing is, in general, if I give you a set of moves that you can apply this move, that move, there could be millions of permutations of those operations. Maybe something as simple as going left or going right. Those two symbols, left, right, can be combined in so many ways. But we cannot work out the exact path in each case. But if there is an invariant which is guaranteed to stay constant, that no matter you go left or right, some quantity x is going to be fixed. Then it doesn't matter whether you do that move 1 times or 1 million times. The starting value and the end value will be identical. Okay, so invariants are very important for that. Then extremal principle. So this is the idea that when you are faced with a problem that you want to find some quantity or you want to maximize some quantity, that typical thing like let's say on a chessboard you want to place as many rooks as you can so that they don't attack each other. So you always go to the extreme case that try to place the highest number of rooks, like what you can call greedy algorithm. So in a way, another name for this is greedy algorithm. So try to force the maximum possible benefit out of the situation, but that is not a proof. So this is where people make mistake that somebody, for example, on a chessboard, somebody 8x8 chessboard. Obviously, you know you can place 8 rooks, right, such that they don't attack each other. And now somebody comes and says that now I cannot place a ninth rook no matter how hard I try. Therefore, nobody can place 9 rooks. So that is the mistake people may make. That just because you are not clever enough to come up with a 9-loop configuration doesn't mean that it doesn't exist for anybody else. Okay, so the proof that you give has to be exhaustive. So it has to show that no matter how clever you are, you cannot place 9 loops on the table. Okay, so you have to be careful. When I say this is a principle, this is not a theorem. So this is how you can derive or find out the configuration. But to actually prove it, you have to use some other idea. Okay. Then there are some other ideas also, like coloring is there, etc. Coloring, tiling. That is more like specific to if you geometry, 2D geometry of any kind, or not true. Actually, coloring can be applied in any other case also. But and finally, graph theory. So graph theory is again, this is not the XY coordinate graphs, but these are different mathematical objects which are like points, nodes, vertices which are connected to each other, etc. Okay, and actually I briefly showed you a glimpse of graph theory. If you remember when I did that prefix free coding. So if you remember that tree which I constructed at 0, 0, 1, 1, 1, etc. So that was nothing but a graph. Okay, let me think. Maybe if I think more, I can add a few points to this. But roughly speaking, these are the overall things you require in non-enumerative combinatorics. Some techniques are like this. So, I mean, to be honest, the difficulty in combinatorics is that there is no theory to teach us. See, in geometry, at least there were a few properties, theorems which you may have not studied so far. In combinatorics, I walked you through all the ideas. That's all there is to teach. There is nothing more I can teach you. Yeah, maybe here there are things to teach. In the enumerative part, there are things to teach because there are like this extension of the existing ideas, etc. But in non-enumerative, there is really nothing to teach. But so therefore, the focus is more on problems and much more heavily on problems. So it is like 5% teaching, which we will finish in no time, and 95% is the problem solving. Okay? So I think combinatorics is the topic where your experience is the most important tool. So the more time you spend solving problems, the more you will be adept at it. There is no magic formula that if I teach you this topic, suddenly you will start getting combinatoric problem. Unfortunately, it doesn't happen. So it's all problem solving. So we'll be only doing problems all the way, to be honest. So next at least 4 to 6 weeks, I'm thinking that we will keep on solving lots of combinatoric problems, and through those we will explore all of these themes. That how do you spot that there is a chance to apply invariant? How do you spot that there is a chance to do some coloring or tiling? So spotting those opportunities is the learning for us. The theory itself is not, there is nothing to learn. So it is all about looking at the problem, finding the pattern and applying the relevant idea. Okay. And just as in geometry, there will be multiple solutions many times. So anything that you find out with different strategy, I'll encourage you to share it with everybody. But as I said, in geometry, in combinatorics, you have to be most careful that you are not misleading yourself and then others by thinking that you have a proof, but it is just a example, or it is applicable to only one set of cases, but not to all cases. Okay. So with that introduction out of the way, we just start by sharing some problems. Oh, also one important thing I did not mention. So I mean, so these two branches of combinatorics, right? Enumerative and non-enumerative. Which one should we do when? Which is more important? Which is less important? As you can guess, like if you have purely objective exam like PRM or IOQM, it will almost entirely be enumerative combinatorics. You can be clever and put a non-enumerative problem also as an enumerative one, like simply pigeonhole principle, right? If you have 10 boxes and you are putting 11 objects, then like some numerical example can be worked out. Like, what is the minimum number of objects required so that each box has at least 2 objects or anything like that. But mostly there will be counting problems. So pre-RMO, IOQM, and even RMO, I would say, can have counting problems. But as soon as you go to INMO and higher, right, the chance of getting a counting problem goes down rapidly, like almost to zero. So INMO and beyond, I would expect that the focus is on non-enumerative combinatorics. So in a way, because right now we are not given any exam, we have to start with the IOQM stuff. So we have to do this counting things first, and then we'll go to the non-enumerative thing. But I'm actually going to shuffle it. So I'm not going to do only counting, and then do this non-counting thing. I want to keep things a bit mixed. So I'll do problems of both types once in a while. Okay. So today, in fact, I'm going to start with the non-counting end of things. Okay, so I'm going to study some problems, give you some problems which are of this kind, and then maybe another couple of weeks later, I will give you some counting problems. Okay, so there is no particular order in which I'm starting, but just for the sake of it, I'm going to start with some ideas around inversion or sorry, not inversion, invariance and extremal principle. And there are only 3 problems right now. I will also require some time to gather more problems and put them in this worksheet, but I will keep updating this problem sheet with more problems eventually. So yeah, I'll give you some time to think about these problems. So question 1, 2, and 3. I think roughly they are in increasing order of difficulty. Okay, so you can first try question 1, then 2 and 3. If anybody has any guess for what is the answer to the first question?
Sir, n.
Okay, you are close. Can you check if that answer works all the time? Like by taking different values of small n. And also, if you are not noted, the question states the interior of the arcs matter. So you are not supposed to count the endpoints of the arcs, only the interior. So make sure you note that point. Okay, does everybody think the answer is n for the first question? Or you have any other suggestion? Okay, so let us see what the diagram looks like for a let's take some case. Like suppose our small n is, and let's take a slightly large value to get some intuition. Let's say n equal to 7. Okay, so then we have 2n minus 1, which is 13 points around the circle. And by the way, in this question, if you think about it, first thing we have to realize what matters and what doesn't matter. The only thing which matters is that there are n objects in a circle. The position doesn't matter, like whether it's a regular polynomial, polygon, sorry, doesn't matter. So it is simply a question of n objects which are around the circle. So I've just taken some 13 objects. So if I call this point A1, okay, and now what is given is that, rather what we want to do, we want to color capital N of these points black. and that coloring is not in our control. So somebody else may be come and doing the coloring. We can choose capital N, but once those points are colored, then out of those some two black points have to have exactly n points in its interior. So for example, if let's say A1 is colored black, okay, then if the desired 2 points are A1 and which point? So if I start calling A1, A2, etc. So then which other point should be colored black for the criteria to be satisfied? Oh, we have taken one more point. Looks like I have a 14th point in my diagram. Just ignore this point. So the wherever that other black point is, the A1 and that point should have in its interior exactly 7 points, right? So basically, if I count clockwise, then A2, A3, A4, A5, A6, 7, so A10. Okay. So if A1 and A10 are both black, then my job is done, right? But of course, that may not happen. Any other, suppose if I consider A10. So if A10 is black, then if A1 is black, it's sufficient. But what other point can I take which along with A10 will satisfy my requirement? So basically here I added from 1, I added how many coordinates did I add? Oh sorry, I should not have taken A10. I want 7 points in the interior. So 1, 2, 3, 4, 5, 6, 7. So A9. So I have to color A9 black. So I jumped 8 coordinates ahead, right? From A1, I jumped 8 coordinates to get A9. Okay. So I'm just joining these two here. Now from A9 again I can jump 8 coordinates ahead. So like that, you see I can complete a cycle of jumping 8 coordinates at a time. And so that will form a like a basically will look like a star. So maybe something like this. Maybe it's easier to jump back 4 coordinates.
Sir, it should be A3, I think.
A3. The goal is the between A9 and A4. I should have. So no, it should be A5, right? Not A3. If I choose A5, then in this
Yes,
part.
sir, A5.
Okay. So basically, I think it's easier to go anti-clockwise and jump 4 coordinates at a time. So A9 to A5.
So I
Sir, I
think it is A4 only.
Yes.
A10.
I think it is A4 only.
Is it A4?
Yes,
Yes,
sir.
Yes, sir, A4.
A10, A11, A12, A13,
Oh,
A1, A2, A3.
okay. I deleted. Yeah, I deleted 8, 10 entirely by mistake. Okay, so A4 is correct. Okay. So like that, I can keep going back. So every time 1, 2, 3, 4, 12, etc. So I can keep going back. So the first question is that when will this cycle complete? Can you tell me when will, so eventually this will return to A1, right? In the process, will it visit all the points or not?
no, sir.
It will not visit all the points. Why is that? Right.
Sir, A12, then A7, and then A1.
No, from A7 it will go to A2, right? So what is the formula? So if you are AI, what is the next step? You have to add how much to the index, so that there are exactly. So if AI is your first point, then in the intermediate I want exactly n points. So AI plus 1, AI plus 2, etc. AI plus small n. So all of these points should be in the middle. So the point after that is AI plus n plus 1. This should be my next point, correct? And all of this is modulo 2n-1. So this is like modulo 2n minus 1. So whether this percentage sign is a relic from programming, then the mod operator is percentage. Sorry, but anyway. So from AI, I have to jump to AI plus n plus 1. So my jump is of size n plus 1, correct? So if I start from A1, or if I just call it 1, so and n is 7, so I have to keep going by steps of 8. And you see that 8 is co-prime with 13. So therefore, this cycle will only complete after it has visited all the points exactly once. Does that make sense?
Yes, sir.
Okay. If this number were not co-prime with 13, then the cycle might complete early. So can you find what is the condition on this number n, small n, under which the cycle will complete visiting all the points, and in this case it will not complete visiting all the points? Okay, so here we just took an example of n equal to 7, but in general, for any given number small n, what is the criteria under which this cycle will complete with all the points?
If n plus 1 is divisible by 2n minus 1.
Oh, you have to say the other way, right? 2n plus 1 is divisible by n plus 1.
Yes, sir.
But that will never happen, right? When will n plus 1 divide 2n minus 1?
Sir, when 2n minus 1 is divisible by 3.
When 2n minus 1 is divisible by 3. Okay. How did you arrive at this?
Sorry, when 2n minus 1 is not divisible by 3.
So if it is not divisible, then the cycle will complete. That's what you're saying? And cycle visits all the points. And if it is divisible, then it may not. Okay, but why? How do you arrive at this?
Sir, n plus 1 divides 3.
Or n plus 1 divides 3. Okay. So no, you want to say 3 divides n plus 1, not n plus 1 divides 3. N plus, what is the meaning of A divides B? A is a factor of B. Okay. So you want to say 3 divides n plus 1, correct?
Sir, when n plus 1 divides 2n minus 1, then n plus 1 divides 3.
I'm not able to follow you. If n plus 1 divides 2n minus 1, firstly, how will this happen? What is the meaning of A divides B? N plus 1 times n plus 1 ones are n plus 1. N plus 1 twos are already 2n plus 2. So how will this ever happen?
Sir, we don't have to divide actually, we have to take the GCD.
GCD, that is correct. So what you want is the GCD of n plus 1 and 2n minus 1 has to be equal to 1. Is that correct?
Yes, sir. So this GCD is equal to the GCD of 2n plus 2 and 2n minus 1.
Correct.
So this is equal to GCD of 3 and 2n minus 1.
Correct. That is. Or you can also, so here you eliminated n plus 1. You can similarly eliminate 2n minus 1 from this equation also, because this GCD will also be equal to no, sorry. Okay, can you, I don't know, maybe you can do that. But yeah, this is correct. So basically, if the GCD of n plus 1 and 2n minus 1 is 1, it means that, so if 3 divides 2n minus 1 or not, that is the criteria. And you can see effectively going mod 3, this means that n has to be congruent to 2 mod 3. And in this case, n is not congruent to 2 mod 3. Are you familiar with this notation? congruency in number theory?
Yes, sir.
Okay. It will simply mean that n gives a remainder of 2 1 divided by 3. Okay. But but I hope everybody followed why did we take this GCD in the first place, n plus 1 and 2 n minus 1, because what we observed here that our step size is of n plus 1. So if I'm starting from 1 and I'm going in increments of n plus 1, n plus 1, etc., then if n plus 1 and 2 n minus 1 are co-prime, then this cycle will complete only after I return to 1, after I visit all the points and return to 1. Okay, so that is why this GCD was important. Okay, so then this means that we have two cases to consider, right? So let's take case 1, probably the simpler. Let's take the case of 3 does not divide. Okay, so 3 does not divide 2 n minus 1. Therefore, what is guaranteed is that the cycle a1 plus n plus 1, then a1 plus 2 times n plus 1, etc., will finally end up at a1. Okay, so in the diagram it will look like some kind of a star, like that. Some star which will finally end up at a1. Okay, so then what? Then what do we do now? What we want to show finally is that we want to choose this number n such that if I color any of these points black, then now it is enough to say that some segment of my star has to have both endpoints black, correct? If both endpoints of one of my segments is black, then the problem is done. So if I color all the points of my star black, obviously that will happen. But the question is, what is the minimum number of points I have to color black for that to happen? So here actually some understanding of graph theory is useful. So we will study graph theory more properly later on. But understand that these points which are like connected to each other, right? My diagram is a bit. Let me take a smaller case. Maybe just take 5 points, okay, for example. So this, you see that these 5 points and these 5 points, the geometrically speaking, this is a pentagon. Okay. But you see, I can just rearrange the points in this way. So geometrically, I have destroyed all the properties. The length of A1, A3 is not the same, but what matters is adjacency. Okay? So adjacency means which vertex is connected to which other vertices. So you see, these two diagrams are identical in that way, because in the first diagram, A1 is connected to A3 and A4. Here also, A3, A5, A5 A2. So you see that each vertex A1 is connected to A3, A4, A2 is connected to A5 and A4, etc., etc. So all the properties of neighborhoods are preserved. Okay, so in graph theory, this is called isomorphism. We'll study this properly later on, but the idea is that the set of vertices is identical and the set of edges is identical. So basically, if in the original diagram I have a segment joining two vertices A and B, then in the new diagram I have another segment joining A dash B dash. There is like one-to-one correspondence between the two diagrams. Are you able to follow this?
Yes.
Okay, so then what does it mean for our problem? So instead of looking at this complicated star, we can just look at a simple cyclic arrangement. And now the question is, how many vertices do I need to paint black, which guarantees that two consecutive vertices will be of the same color. So now in this term, do you see what is the answer now? So if the original, so all of this is under the assumption that 3 does not divide 2n minus 1. Okay, so the original complicated star will have 2n minus 1 vertices. When I unpack the same star into a nice linear structure, like a simple polygon, it will still have 2n minus 1 vertices, but the order may be different. So I want to write the coordinates here, so it doesn't matter. But you still have 2n minus 1 vertices. So in fact, the ordering, the labeling doesn't matter. So we can take without loss of similarity, we'll call this A1 and 2 A3. Doesn't matter. And the last vertex is A2n minus 1. Okay, so suppose you have such 2n minus 1 vertices. How many of them you have to paint black to guarantee that 2 adjacent one will be also black? So this is where you can think of using extremal principle, because the idea is you have to have a greedy algorithm that you will try to paint as many vertices black as you can. Okay, so actually I should have drawn this diagram in blue, but anyway, there's yeah. So for example, if I choose A1 to be black, now I cannot choose A2 black. Okay, then I can choose A3 black, etc. So suppose I want to fail. So then how many maximum? So I am answering the contrapositive question that how many maximum vertices can I paint black without getting a single adjacent segment black? So obviously I can follow an alternate pattern, right? Every alternate vertex I can paint black. So all the odd number A1, A3, A5, etc. All of the odd ones are being painted black. And so do you see where the problem will come at the last vertex, right? Because this last vertex A2 and so if I paint this black also, then I have constructed my segment. Okay, so how many black segment black vertices are painted here? I think the answer is n, right? So my claim is that if sorry, not capital N, I'm going to say small n. So if n is greater than equal to n, or in other words, if I paint smaller number of points black, then it implies that there exist two adjacent black vertices. So how do you prove this? Okay, so you can do this with the pigeonhole principle. The idea of pigeonhole principle is you have to identify which are the boxes and which are the objects. So can you suggest what can be the boxes over here? What is pigeonhole principle? Can somebody tell me the statement?
There are n object, n boxes and n plus one objects, then at least one box has to have more than an object.
Yes, correct. And so that's what we have to do here in a way, right? The painting the black vertex is like putting that object in the box. So in some box, I want two vertices which are both black. So if I paint more than small than vertices black, I want some two of them to be adjacent. So does that suggest to you what should the boxes be in this case? How about this? Let us consider the boxes as A1, A2. So every pair of vertices are put as a box. Dot, dot, dot. So in general, A2k minus 1 and A2k. This kind of pair. And the last pair in this ordering will be A2n minus 3 and A2n minus 2. And finally, I'll be left with a single element A2n minus 1, which has no box. Okay. So how many boxes have I created here? Ignoring the last element, how many boxes do I have?
2n minus 1.
No, n minus 1, right?
Yes, sir, n minus.
N, because each box has 2 elements. So I have n minus 1 boxes. Okay. So now there will be two cases here, whether or not we paint this last number or not. So case 1, we don't paint the last vertex as black. So which means so we are already saying the claim, all of this is under the assumption that I am going to paint smaller number of points as black. So then if the last vertex is not going to be painted, then basically the n black points are all going to come from these n-1 boxes, correct? So do you see right away this would imply that there exists some box with 2 black vertices. And that will be the contradiction, correct? Because any box which has 2 black vertices are going to be adjacent. So this case is over. So if we don't choose to paint this last vertex as black, then the remaining n-1 boxes cannot accommodate the n black vertices. Then case 2. So in other words, we are forced to paint the last vertex as black. Okay. So A2n-1 is black, that is given to us. Now what can we say?
One vertex from each box has to be painted.
One vertex from each box has to be painted black. But then what's the problem, right? We are not getting contradiction.
Sir, but then it will still come out to be a contradiction if we look at it. If we take that situation, then if we paint that A2n-1, then in the box A1, A2 will be black. And then if we complete the circle, A2n-2 will be black. So A2n-2 and A2n-1 are adjacent and black.
Yes, correct. So basically A2n-1 is black. Now exactly all the n-1 remaining vertices have to come from 1 of each box. Any box has 2 vertices, immediately it is over. So therefore, out of A1 and A2, some one of them has to be black. And A1 cannot be black because it is adjacent to A2. Therefore, A2 is black. Similarly, out of A3, A4, A3 cannot be black because it is adjacent to A2, etc. So like that, you are forcing the entire even cycle to be black. A4, A6, A8, etc. And in that process, the last vertex A2n-2 will also be black, which is adjacent to A2n-1, and we are done. Okay, so what we have proved is that if we paint a smaller number of points as black, then it is guaranteed that some 2 black vertices will be adjacent. Does everybody follow this argument?
Yes.
Okay. This is fine. I'm going to show you something very different way of looking at the same question. So what was the conclusion of the case 1, that this last vertex cannot be painted black? Sorry, it has to be painted black. So whichever was the left out vertex, A2n-1, that has to be painted black, correct? But we created these boxes, right? So for the same geometry, who stops us from creating a different set of boxes? Okay, so let's say I'll use some colors here. So let's say first time I create the boxes like this. Okay, so this was my left point, and the conclusion is that this has to be painted black. So we understand that. But I can come up with a different grouping like this. Okay, so now this vertex is left over. So now repeating the same point of case 1, it means that this vertex also has to be painted black. And you see basically by without loss of generality, see these labels A1, A2, A-1 we only chose. There is nothing special about them. So the conclusion is that the same idea can be applied to every single point. So all the points have to be black under that logic, which cannot happen. So that is the contradiction. Did you follow this idea? That this creation of the boxes was completely in our control. No matter how you paint the vertices, right? I can apply any grouping I want. So first time I apply a grouping where I keep A2n-1 alone. And then the conclusion is that if there is no set of adjacent vertices, black vertices, then A2n-1 has to be colored. But in the same way, I can take one configuration where A1 is left alone and I make the grouping like this A2, A3, A4, A5, etc. Then again, by the same logic, what it means that A1 also has to be colored black. Similarly, A2, A3, all of them have to be colored black. Only in that case, you will not get this contradiction. Okay. You know what? I think I'll go and write this properly later on because I hope you are able to follow what I'm saying here. But as I said, that it's important to not only follow the logic, how you represent it is also very important. So in combinatorics, particularly, I will urge all of us to spend a lot of time, including myself. I would like to take some time to write down the solutions and share them so that we can review and improve our writing style. Okay? Because clarity of presentation is very important in combinatorics. I cannot stress this enough. Like while checking the RMO papers, I have to tell you the most disappointing or disheartening thing for us is that we see in the rough work that the student has got the idea correct, but they are not able to write it properly. So it is very hard to give a lot of credit in that kind of question. But anyway, we are almost out of time. I mean, right now we covered the case of this 3 does not divide to n minus 1. In the same way, we can do the other case 3 divides to n minus 1. Okay, so I'll encourage you to try this at home and we will discuss this next time. Okay, but yeah, I mean, we are switching gears quite a bit from geometry as you realize that geometry we were thinking in a very different manner. In combinatorics, we have to think quite differently. So we have to get prepared for that kind of situation. Okay, we are almost out of time, but let me just quickly make some progress on the puzzle from last time. So this was about error correcting codes actually. And the very simple thing that we did was that suppose I am transmitting a message of 4 bits, maybe 0011, and I want the receiver to know that whether some error happened or not. So we added a 5th parity bit, which was simply the sum of the first 4 bits modulo 2. Okay. So for example, here I transmit 0. So the receiver knows that suppose the receiver receives the message 01110. So then they can work out that the sum of these 4 bits is not equal to the parity bit. So some error has happened. So this is simply error detection. But the receiver has no idea where the error has happened. So typically he will ask the sender to send a message again. But if we can correct the error, that we know exactly which position the error happened, that would be amazing. Right? So for that, what we can do? So it is almost like a TKP. So this idea of detection is only what we want to use. And this goes all the way back to, if you remember, the prisoner problem. 1,000 bottles, there is a poison bottle. Do you remember that problem?
Yes, sir.
So there, what had been done? Again, the question was that whether or not there is poison in this bottle. We want to find out which bottle particularly had the poison. And the trick we used was that every prisoner was given a different combination of these bottles. So then we know which prisoner dies and which survives. That gives us a unique pattern, which tells us that which person was the which person had the poison or which bottle had the poison. In the same way, suppose I have 4 bits. You see, I can here the parity bit just added up all of them, which is not that useful. So suppose I combine them cleverly. So for example, first I take the parity of B plus D only, and then I take the parity of C plus D. Okay. So these are the 2 bits I'm transmitting. So now instead of one bit, I'm going to transmit 2 bits. So A B C D followed by B plus D and C plus D. And so now you can see that take the same example. So suppose I transmit 0011. So now by this logic I have to add what? So B plus D, which is 1, and C plus D, which is 1 plus 1, but modulo 2 it is back 0. So I'll transmit this sequence 001112. Okay. Now suppose something went wrong and one of the bits got tampered, this one. So the receiver actually received the message 011110. Now what they can do, they know this scheme, they know they have used this kind of encoding for the error. So they know that the sum of B plus D should be equal to this bit. But is it the case? It is not the case. So which means that B or D has the problem. Then they go further and check the C plus D. So is C plus D and this matching? It is matching. So C and D don't have the problem. So then if one of B or D has a problem, but it's not B, so it means that B is the one which has the fault. So then the person can know that this is the place where the error has happened and they can correct this. Right? So then the original message which was 0011 has been recovered. Okay, so this is error correction. And as you can imagine, here I give a very toy example, like 4 bits. For that we require 2 extra bits. As it turns out, I mean, this is seem very wasteful. That like when I wanted to transmit 4 bits, I have to transmit 6 bits instead. So I have to add like 50% extra information, which is seems very large. But as you see, this grows. If this doubles, this has to increase by only 1. Okay. So in general, if I'm taking nth power of 2 raised to n, will require only n bits to be encoded. Okay, so the amount of information grows much faster than the amount of extra error bits I have to put. Okay. So in the long term, this scheme turns out to be very efficient. Okay, so I'll encourage you to think about how to design this further. So instead of 4 bits, suppose I have 8 bits of information, then how many bits I should add, etc. I'll suggest you to think about that also. Okay, I think that's all for today. Thank you. Bye.
Thank you so much, sir.
Thank you, sir. Bye, sir.
Thank you, sir. Bye.